I'm Jason Lee from CMU, and this talk will be on Approximate Gomory-Hu tree in roughly Maxflows time to appear in STOC 2021, and this is joint work with Gomory-Hu from Duke. In this talk, all graphs will be unweighted and undirected, and we'll be considering a host of close related problems. The first is the Gomory-Hu tree problem, which is to compute a tree on the same set of vertices as the graph, such that the min cut in T of any two vertices U and V equals the min cut in G of U and V. Gomory and Hu show that such a tree always exists for any graph, and they showed an algorithm to compute such a tree in n-1 Maxflows calls. Surprisingly enough, even after 60 years later, this remains the best running time for general graphs. And improving upon it in any way would be a major breakthrough. There have been some improvements for unweighted graphs. For example, the m-n time algorithm of Balgat et al., and also an improved running time for sparse graphs by Abood, Krauthammer, and Trabelsi. Another problem we'll consider is the single source min cut problem, which is given a source vertex S, find all the min cuts from S to V for all other vertices V. And recently, Abood, Krauthammer, and Trabelsi showed that this can be used to compute a Gomory-Hu tree, which is why this problem is now interesting. In this talk, our main results are about approximation versions of these problems. And recently, Abood, Krauthammer, and Trabelsi showed that the all pairs min cut problem in this approximate setting can be solved in quadratic time, which is significantly faster than the best exact algorithm. And this motivated the study of approximate versions of these problems. However, for computing a Gomory-Hu tree, nothing was known before our work. And in our work, we show that we solve the approximate Gomory-Hu tree and single source min cut problems in roughly exact Maxflows time. That's Maxflows time times some polylog factors. This is m to the 4/3 time for unweighted graphs, and m plus n to the 1.5 time for weighted graphs, which is a fair improvement over the previous best n squared. All of our results are based on a new primitive that we introduced in our work called the cut threshold problem. This is given a source vertex S and a parameter lambda called the cut threshold, we want to output all vertices whose min cut from S is at most lambda. So think of lambda as a cut threshold, and we want to output all vertices whose min cut falls below that threshold. We first provide an algorithm for the cut threshold problem in roughly Maxflows time, and then we show that cut threshold can be used as a primitive to solve the approximate single source min cut problem. And by a reduction of Abood, Krauthammer, and Trabelsi, this also implies an algorithm for approximate all pairs min cut. Finally, with some more work, we show that cut threshold can also be used to solve approximate Gomory-Hu tree, well, again, in a very similar running time. Before we get to the cut threshold algorithm, we first introduced an important subroutine that we'll use to solve it. And this is called the minimum isolating cuts. This is a problem where we're given the graph and a subset of terminal vertices. We want to find for each terminal vertex the min cut that isolates that terminal, that separates that terminal from everyone else, from all the other terminals. So in other words, this set SV is the V, R minus V min cut. It's actually the side of this cut that contains V. So this problem can be trivially solved in R many ST min cuts. That's because we just need to solve the V, R minus V min cut for each V. But surprisingly, we can do much better. We showed in recent work of myself and Gomory-Hu, we showed that actually log R many SE min cuts suffice. And this was first observed while we were trying to solve the deterministic min-cut problem, which is what this work is about. At this point, let's first develop some intuition on this minimum isolating cuts problem to see how it can be used to solve various other graph cut problems. As a warm-up, let's first consider the global Steiner min-cut problem, which is given a graph and a set of terminals. We want to compute the min-cut that separates at least two terminals. So here, for example, we said let S be the global Steiner min-cut for this set of red terminals. Now consider sampling a subset of terminals and running minimum isolating cuts on that subset of terminals. If we get lucky and exactly one vertex that we sampled is in S, then observe that the minimum isolating cuts for this subset of terminals is going to include S. That's because S is a valid isolating cut around this vertex, and any isolating cut is also Steiner cut, and so therefore the isolating cut around this vertex must be the Steiner min cut, and which is S. So in this case, we just compute the minimum isolating cuts and compute the sizes of each of the isolating cuts. Then one of the sizes will indeed be the global Steiner min cut. And what is the sampling rate at which we would get exactly one vertex in S? Well, we should be sampling at a rate roughly 1 over the size of the intersection of S and R. That's because with this sampling, with constant probability, we sample exactly one vertex in S. And finally, in order to guess the right sampling probability, we simply sample at geometrically decreasing rates. So 1/2, 1/4, 1/8, and so on. One of these will be within factor 2 of the right sampling rate, and that's will be constant factors of S. So this example shows how random sampling can be used alongside minimum isolating cuts, and we'll be following a very similar routine in our cut threshold algorithm. So let's now proceed with our cut threshold algorithm. For this problem, we'll make one small change in the problem statement. We're given an additional subset R of vertices, and we only need to certify the vertices in R that are min cut at most lambda from S. Of course, for the original cut threshold problem, we'll simply set R to be B itself. So it turns out our cut threshold algorithm is essentially what we should expect if we were to adapt the Steiner min cut algorithm to this problem. So once again, we try each sampling rate from 1/2, 1/4, 1/8, and so on, except we make the distinction that S, the source vertex, is always sampled. And for each sample, we compute minimum isolating cuts on this sample. And finally, we take the isolating cuts, and if any of the cuts is for each cut of size at most lambda, that cut certifies that the terminals inside the cut have min cut at most lambda from S. So essentially, we're just computing a bunch of cuts, and for any of the cuts of size at most lambda, we can certify the vertices on the other side, not S's side, the other side, have min cut at most lambda. And by just computing a bunch of cuts and certifying things inside, we hope to get most of the vertices that can be certified. And indeed, we show such a thing. Our main claim is that we can certify in expectation some 1 over log n fraction of all the vertices that can be certified. Now, assuming this claim, the final algorithm for cut threshold will simply be to repeat this cut threshold step algorithm some log squared n times, where for each iteration we call cut threshold step, where R is all the vertices that are still uncertified. That means that after log squared, by this claim, after log squared iterations, we have that with high probability, at the end of all these iterations, the remaining set of vertices that are uncertified is exactly the set of vertices that cannot be certified. So anything that can be certified, we already certified, and therefore we have the correct output. Let's now develop some intuition on why this statement might hold. So let's first fix some certifiable vertex. In other words, a vertex in R with min cut at most lambda from S. Let big S be the V side of the min cut between V and S. And now, once again, suppose we can sample this time exactly V in S. So suppose we sample V, but no other vertex in S. Then, once again, observe that in that case, the minimum isolating cut around V will be exactly S. So in other words, S equals SV for the minimum isolating cuts procedure. Now, what is the probability that we get lucky and that happens? Well, suppose we sample at a sampling rate roughly 1 over the size of S intersect R. Then with probability that, we sample V. And with constant probability, we don't sample anything else inside S intersect R. So that's an overall probability of roughly 1 over S intersect R. Now this probability might look small, especially when S intersect R is large. But observe that if we do get lucky, then we actually certify all the vertices in S intersect R. So that means that in expectation, we certify the probability times the number, which is roughly 1, like a constant. Now finally, this analysis can be repeated for all the vertices V that are certifiable. And if we sum over all V, the expected number of vertices that we certify is roughly within a constant factor of the number of vertices that is certifiable. Now this analysis almost works, and except for one main issue, which is a vertex may be certified over multiple different V. And in that case, we're counting the vertex as being as certified multiple times, when we should really only count that vertex as certified once. So there's an overcounting issue, but we'll show next that it's not too bad. In particular, so here's the algorithm once again. And in particular, we show that with high probability, each vertex is overcounted only some log n times. Now for the proof, we'll consider the collection of all ST min cuts for all t of size at most lambda. And we'll use the fact that this set of cuts form a lambda family on the set of vertices. Now let's fix a vertex V. And let's first count in expectation how many times the vertex V can be certified, how many times it can be overcounted. So for each vertex, so for each of the first 3 vertices, the relevant sampling probability is around 1/3. And in order for this vertex to certify V, to be responsible for certifying V, it must in particular be sampled in the subset, which happens with probably roughly 1/3. So each of these 3 vertices, each gets sampled probably roughly 1/3. And similarly, these vertices, for these vertices, the right sampling rate is 1/7 because this cut here has size 1/7, size 7. So we get 1/7 probably for each of these, and so on. And note that now observe that this sequence is dominated by the harmonic series, which has sum roughly log R. So in expectation, we get the expected number of times V is certified is roughly log R. And finally, we want with high probability bounds, so we want to apply Chernoff bound. We apply it to the events of whether each vertex is sampled at its correct sampling rate. These events are independent among different vertices, and therefore we can apply Chernoff bound and get log n times, get overcounted log n times with high probability. So with the cut threshold algorithm, the single source min cut algorithm is then fairly easy. We simply run the cut threshold algorithm at scales of 1 plus epsilon. And the approximate min cut of each vertex ends up being the smallest scale at which it can be certified. Now the Gomory-Hu tree algorithm is more complicated. It follows Gomory and Hu's original recursive approach, except here we're going to branch multiple times in each recursion step, where the sets that we branch on, the cuts that we compute, are among the isolating cuts that we get from the cut threshold algorithm. There are a few more details, such as we need to sample the source S uniformly at random. This is a technique borrowed from Abood, Kartheimer, Trabelsi. And finally, controlling the approximation factor turns out to be non-trivial and requires some work. But due to time constraints, we won't be covering these additional steps. In conclusion, we provided algorithms for cut threshold, 1 plus epsilon approximate single source min cut, and 1 plus epsilon approximate Gomory-Hu tree, all in roughly exact Maxflow time. And our main tools were minimum isolating cuts together with a simple random sampling. As for open problems, perhaps the most exciting open question is whether a faster exact Gomory-Hu tree exists. So our work actually implies that this reduces the computing faster exact single source min cut values. That's just for each vertex, compute the size of the single source min cut, not necessarily the cut itself. So that's just a table. The output is just a table of n entries. Unfortunately, even that problem, we don't know how to solve faster than just simply trivially running n-1 Maxflows. But any improvement upon this would imply an improvement upon exact Gomory-Hu tree, and the single source min cut values problem seems simpler and more approachable than the Gomory-Hu tree. So that's one direction we could take in the future. Another direction is concerns the fact that we're reducing approximate Gomory-Hu tree in our algorithm to exact Maxflow, which is not ideal because we should really be reducing to approximate Maxflow. But there are fundamental reasons why we use exact Maxflow, and this comes from this isolating cuts procedure. Now, if we can somehow reduce the approximate Maxflow instead, then we can use the near linear time algorithm for approximate Maxflow, which is known. And this will give approximate Gomory-Hu tree in near linear time. Finally, I'm always excited to see what other problems minimum isolating cuts can be used to solve. So far within this year, I've seen at least like 4 to 5 results. I'm curious how far this technique can be pushed in the future. And that concludes my talk, and thanks for listening.